All right. Hey, everyone. We are going to switch gears a little from talking about planets to talking about light, which is a very important topic for astronomy. Almost all data we get in astronomy actually comes from light. So, knowing about light and how to interpret it is really essential for an astronomer. So we'll start off with kind of a fundamental question, right? What is light? What's its fundamental source and how is it produced? So we can think of light as a wave, kind of akin to mechanical waves. So mechanical waves are kind of like this ocean wave here. They carry energy through a medium without completely displacing that medium. Waves can be characterized using four quantities, right? Wavelength, frequency, amplitude, and speed. So frequency is how many cycles per second. So it can be like 1/second, or hertz is the unit. Wavelength is the distance from wave crest to wave crest, right? So the top of the wave to the next top of the wave. Amplitude is the displacement vertically, and speed. Um, this is maybe self-explanatory, how fast the wave is going. So waves can interfere with each other or, add together. They can refract or bend. They can reflect or, bounce off a surface, and they can diffract, which basically makes the wave look like it's coming from a new source. So Dr. Hassel has some great demonstration videos, which I will link to in this module. So I'd really encourage you to watch those to really get a sense of how all of these things kind of work, how interference, refraction, diffraction, and reflection look in real life. So unlike mechanical waves, light has a constant speed, right? It's about 3 × 10⁸ meters per second. So this is often called the cosmic speed limit. Nothing can go faster than this. It's denoted often as c, the speed of light. So this is determined by the wavelength and the frequency. So we get c is equal to lambda, which is wavelength, and f, which is frequency. So wavelength, remember, is how far apart the wavefronts are, and frequency is the cycles per second and is actually associated with the color of light, right? If we were talking about sound as a wave, or yes, a sound wave, frequency would be kind of the tone or the pitch. But for light, it is a little bit different. When we talk about frequency, we're talking about the color of the light. Another difference from mechanical waves is that waves, like water waves, they travel through a medium, right? So like that ocean wave I showed earlier, we have a wave kind of traveling through the medium of water, right? Sound travels through a medium of air. But we know that light can actually travel just through the vacuum of space. So what exactly is the medium that light goes through? So light is an electromagnetic wave. It gives off oscillating electric and magnetic fields that are perpendicular to each other and perpendicular to the direction of travel. So this is kind of a schematic of what that means. So we have kind of a demonstration of wavelength, right? Basically from peak or trough to peak or trough right here. This is the wavelength. Uh, this red line is the direction in which the wave is traveling, and the black is the oscillating electric field. The blue is an oscillating magnetic field, and this drawing is trying to show the kind of the orthogonal or perpendicular nature of these waves. So because these are fields, right? We have an electric field and a magnetic field. So this means that light can travel basically through empty space. So light doesn't need a medium like those waves in the water or the air need. Light can also be broken up into different wavelengths, so different components of light called a spectrum. So you can do this by sending light through a prism or a grating. And you might be familiar with this. You might have those little prism, like decorative prisms that you hang in windows and it projects a rainbow. Or you may have just seen a real rainbow, right? Drops of water can also act like a prism and it breaks the visible light up into the many colors that we are familiar with a rainbow. And so on your screen here, you can kind of is trying to demonstrate the different wavelengths of light that we see. So red light has a very long wavelength, and as we go down, those wavelengths get shorter and shorter until we get to violet light, which in the visible spectrum has the shortest wavelength. Okay, so that's all for this particular lesson, but remember to watch Dr. Hassel's demonstration videos. I think that will really put a lot of this into perspective and will really show you how it all works. And you can join me for part 2 of our introduction to light.